Okay, we're going to look at the Unit 8 practice test here. So the first one's some matching. We're asking about alphas, betas, gammas, and positrons. So it requires 1 meter of concrete to stop this stuff. Okay, that is the gamma. This answer C. Carries a negative charge, E0, -1. That's our beta particle. Is a helium nucleus. Helium nucleus is an alpha particle, 2 protons and 2 neutrons, flying around. Okay, this one here, we need to have cesium and barium. We need to go look at our periodic table. And cesium is number 55 and barium's number 56. So we need those two numbers. So 55, 56. So we can see our top number is going to be 3730. It must be 0. And if it's 56, this must be -1. So we're talking beta particle, E0, -1. Has the greatest mass of the four. Okay, alpha particles, since they're 2 protons, 2 neutrons, they're about 7,200 times more heavy than a beta, and we know that gammas have no mass. Okay, so it has the greatest mass of the four, that's alpha, and is used to kill bacteria on packaged fruit. Okay, that is just looking at the uses of radioactivity and find out they can jam gamma rays through packaged things and kill the bacteria and therefore increase the shelf life of certain things. Okay, number 2, multiple choice. In a cloud chamber, alpha particles leave longer tracks than beta. No, they leave shorter tracks because they bump into a lot of particles. So it's not A. Gamma rays can be seen when the chamber is heated. No, you can't see gammas because it, so seldom does it interact with matter, it doesn't leave a trail. The dry ice is used to cool the chamber so radioactive particles can be emitted. It does cool the chamber, but not so that radioactive particles can be emitted. They can be emitted either way. The tracks are seen when alcohol condenses on the radioactive particles. Okay, that is our best answer. Okay, that, when the radioactive particle goes through, it leaves little ions, and then the alcohol, vapor, condenses on those little ions that are left, and that's why we can see the track. Okay, when you get to 8, Becquerel, Henri Becquerel was best known for, now not discovering X-rays, because that was Röntgen. Coined the term radioactivity, no, that was Marie Curie. Discovering radioactivity, that's what he did, by accident. And making new elements, no, that was, first was Curie. So, or not making new elements, no, making new elements was happening in modern times over at Berkeley by Al Ghiorso and Glenn Seaborg. Okay, so discovering radioactivity is Henri Becquerel. Which of the following is not an example of radioactivity? Okay, being exposed to UV rays. Okay, that is not. Now that is radiation. Okay, that's the same thing that radiates out, but that is not radioactivity. Okay, using americium-241, yes, it keeps things ionized in a smoke detector. Using gamma rays to check for weak points in a welding, yes, that's radioactivity. And using technetium as a radio tracer, like they did with Mr. Papadakis to check, his circulation. Okay, so those are all fine. So it's answer A. UV is not radioactivity, but it is radiation. Okay, questions 10 and 11. Use the following graph. What's the half-life for the decay? Well, let's start here, and let's call that 180. So when do we get down to 90? Something like there. So that looks like 2, not quite 4, maybe about 3. Okay, between 2 and 3. So I think my best choice here is 4 hours. Okay, now, okay, so it looks like it was, it's 160, 180. It looks like 180, so down to 90. 90 be a little bit there. So 90, okay, so it looks like it's maybe 4. It's kind of pushing it. Closer to 4 than it is anything else on this graph. What percent of the original sample remains after 12 hours? Well, if the half-life is 4 hours, okay, so we're really saying here's T, here's T1/2, here's mass, and here's mass at time T. We're saying what percent remains, so that's this question mark, and this is 100% implied by the fact we're asking about percent. And the time, we're talking about 12 hours, and we're saying the half-life is 4 hours. So that means we have to get the one above it right to get this right. So we say if we start with a 100, Okay, 4 hours and 12 hours, that's 3 half-lives. So it goes down to 50, goes down to 25, goes down to 12.5. So we're looking for an answer, 12.5%, answer B. Okay, question 12. The decay series of thorium involves an alpha decay and then 2 beta decays. What's the result of these decays? Well, we can do this 2 different ways. We can write this, there's an alpha decay, then there's 2 beta decays. We can write 3 separate little equations where we start off with thorium, okay, 232, and then we have to go back and look at, okay, well, what is thorium? Thorium is way over here, number 90. So thorium 90, okay, and it changes into an alpha, and let me figure out what it is. So this is 228 over 88, and 88 is 88 back here is that's 89. Where's 88? 86. Here it is, radium, Ra. And then it goes through a beta decay. So we start over, radium 228 and 88. Okay, it's going to give a beta. 8 is 0, negative 1. And that's going to be 228. And it'd be 89, which is actinium. And then we could do it one more time. Actinium 228, 89. Gives off a beta, 0, negative 1. So we have 228. And we have 90 again, which is thorium. Phew! So the final thing we're going to have is thorium 228, which we just write it like that, Th228. So we need to do 3 separate things on there. Now there is an alternate way to do this, and that is start off with thorium 232, 90, and then give off all 3 particles, just write them all together, 4 and 2, E0, negative 1, E0, negative 1, plus whatever's in the box. Okay, and when we do this, then we can say, okay, I've got 232, 400, so this must be 228. And the bottom 90, 2 minus 1 minus 1. Well, 2 minus 1 minus 1 is 0, so it's going to be 90 again. And that gives us thorium. So we can do it 2 different ways, get the same answer. Okay, thorium 228. Okay, number 13. The isotope decays from 60 to 7.5 grams in 1 hour. What's the half-life? Okay, so let's do our problem here. So we have time, and that is 1 hour. Okay, now the answers are all minutes. So let's call that 60 minutes. The half-life is what we're looking for. The mass at time 0 is 60 grams, and the mass at time t is 7.5 grams. So we know these two, so we're going to draw a picture. We can say 60 goes down to 30, goes down to 15, goes down to 7.5. Okay, so we have 1, 2, 3 half-lives. So if 60 minutes is 3 half-lives, 1 half-life would be 20 minutes. Let's go on to 14. In the nuclear equation, the letters Z and A respectively are. Okay, so here's a problem. We have to figure out what those letters A and Z right here are, and we just have to do our numbers. So 238, and this is 4, so that top number must be 234. And the bottom number Z, okay, 92 and 2, so this must be 90. So we're looking for Z and A. This is Z and this is A. So 90 and 234, and that is answer A. Okay, number 15. Iodine has a half-life of 8 days. What percent would remain after 24 days? Okay, so let's change colors. So we're going to say our time is 24 days. The half-life is 8 days. So we can see we're talking about 3 half-lives. The original mass, since we're talking about percentages, that implies it's 100, and we're looking for the mass at time t. Okay, that's what we're looking for. So 3 half-lives, starting with 100, we're going to go down to 50, we're going to go down to 25, we're going to go down to 12.5%. So the answer is 12.5%, answer A. Okay, let's look at the free response. The decay graph of 8 gram sample of barium is shown below. Okay, what's the half-life? So we started with 8. How long does it take to get down to 4? And again, our graph is a little funky here, so it looks like, I think that's 4. Maybe that's 4. That's 4. Yeah, because 0 would be at the bottom. So how long does that, there, that looks like 1, 2, 3, 4 boxes, that's 10 years. Okay, so 10 years is the half-life. The time it takes to get from, in this case, 8 down to 4. But we'll try to make sure that graph looks good when we do the question. Okay, B, how many years will only 0.5 grams of barium remain? So if we start with 8, okay, then we're going to go down to 4, and we're going to go down to 2, we're going to go down to 1, and we're going to go down to 0.5. That's 1, 2, 3, 4 half-lives. So 4 times 10 years, it's going to be 40 years. Now, officially, what we just did was we said that our time is what we're looking for. The half-life, okay, that was 10 years. The original mass, okay, was 8 grams from the problem before. And the final mass, the mass of time t, is, what do we say, 0.5 grams. So since we knew those two numbers, we drew our picture and figured it out from there. Okay, draw on the graph above the decay of 8 grams, which has a half-life of 5 years. So if we start from 8, we say, okay, at 5 years, we're going to go down to half that much. That's 4, I guess that's right there. Okay, and then we're going to go half from that. It's going to be 2. Okay, after 10 years, and half of that would be 1. And half of that, after 5, 20 would be 0.5. So we're going to get a graph that looks something like this. And again, it would be a little easier if these numbers were correct. But that's the idea. So the data we're going to do, we're going from 8 down to 2, down to 4, down to 2, down to 1, down to 0.5. This is starting at 0 years, and 5 years, 10 years, 15 years, 20 years, and that's what we're plotting. Okay, 17, whoops. 17, cesium undergoes beta decay and releases gamma rays. Write an equation for that. Okay, so cesium, 137, and nicely they put the numbers in so we didn't have to look them up, undergoes beta decay and releases gamma. So beta decay means the beta is on the right side of the arrow, and it also releases gamma. We just have to write that in. It doesn't make any difference to our numbers because it's 0, 0. So the top number, 137, this must be 137. And the bottom, 55. On this side I have -1, so it must be 56. Okay, so 56, we look on here, we've seen that before. 56 is barium. So our answer here is barium, using our periodic table. Okay, second part here, the half-life of cesium is 30 years. How many grams of a 160 gram sample remain after 120 years? Okay, so let's do all our things. We have time, we have half-life, we have the mass at time 0, and we have the mass at time t. Half-life is 30 years. How many grams of a 160 gram sample, so that's our starting, will remain after 120 years, and we're looking for how much is left over. So we know these two numbers, 120 and 30, so that means we have 4 half-lives. So starting with 160 grams, we're going to reduce it by half 4 times. So we're going to go down to 80, we're going to go down to 40, we're going to go down to 20, we're going to go down to 10. So we're going to have 10 grams left after 120 years. Okay, write the nuclear equation for this. Okay, sodium, that weighs 22. Okay, decays to form neon here. Okay, so if that's our starting, then what else has to happen? 22, 22, this must be 0. 11 and 10, this must be 1. Okay, 0 and 1, that sounds like a positron. Okay, so we got a positron decay. And B, if the half-life of this stuff is 2.6 years, how many years will a sample decay to 12.5 That doesn't make sense. So after how many years, there it is. Okay, after how many years will the sample decay to 12.5? Okay, again, so since we're talking about percent, that means that our original mass is 100%, and our mass at time t is 12.5%, and the half-life is 2.6 years. And so we want to know what is our time, what is the total time? Well, we know we're starting with 100%, and after a half-life we'll go to 50%. After a half-life we'll go to 25%. Okay, let me fix that. 25%. And then after one more half-life, 12.5%. Okay, and that's the number we were given. So we have 1, 2, 3 half-lives, so we need 3 times 2.6. Now, if it was 2.5, it would be 7.5, so 7.6, 7.7, 7.8 years is my answer. Okay, for 19, americium-241 is found in smoke detectors. It goes through alpha decay, so write a formula for that. So here's americium-241 over 95. It goes through alpha decay. So alpha decay means it's on the right side, the decay part, and alpha is 4 over 2. So we just do the numbers. The bottom is 93, and the top one, 241, so it's going to make it 237. So 237 over 93. So who's number 93? 93, 93, 93. Down here in the bottom, there it is, Neptunium. Okay, so it's Neptunium using our periodic table, and that's our equation. Okay, a 2-gram sample decays 2.5 to 0.5 grams in 860 years. So what's the half-life? So the total time we're talking about here, let's change colors. Total time is 860 years. Okay, the half-life is what we're looking for. The mass at time 0 is 2 grams. And the mass at time t is 0.5 grams. So since we know those two numbers, we're going to draw our picture. So 2 grams. After a half-life, it's going to go down to 1 gram. And after another half-life, 0.5 grams. So we're talking 2 half-lives. So if 2 half-lives is 860 years, then each one of these must be 430 years to make up the 860. So the answer is 430 years for 1 half-life. And that is the test. 430 years, Neptunium, 7.8 years. Okay, positron particle. Yeah, it looks like we got the right answers. So that's the test. Good luck.